Good morning, everyone. Let's get started and we'll rehash whatever we did in the last few weeks or even last few months. We have last 2 weeks of classes right now. I did promise when we started saying that we will be able to understand how NMR would help you get atomistic information of biomolecular systems. While we will not be able to do the practical aspects of it, I'll be able to help you understand how the theoretical origins that we have been discussing would help you build up experiments or understand experiments that have been built up to study larger systems like biomolecules. Okay. Before going ahead, I would like to entertain any questions that you guys might have had. You've been sitting on multiple 2D experiments for the last few weeks. If you thought about it, if there is a confusion, if something is unclear, please make use of this opportunity to ask any questions.
Hardware.
NMR hardware. I see. What's your question on NMR hardware?
There was a point in locking process in which you said that internal circuitry keeps the frequency constant while V naught varies by providing some little amount of current. So V naught varies at each point of time. So how it is decided that what amount of current it is providing?
Okay, so the question that's being asked is how does locking work and how does the current that's given back to keep the field frequency lock works? The V naught is not supposed to change too much with time, but there are some minor fluctuations that happen as a function of time. How does it do it is that it uses the deuterium frequency. Let's say that when the experiment begins, just for instance, the deuterium is set at 70.0356 megahertz, just for instance. Okay. So when you have it set at this, what it tries to do is that any changes that happen, so let's say it becomes 355, it adds up current to make it 356. On the other hand, if the 356 becomes 357, it reduces a certain amount of current. Remember, current is magnetic field, right? If you have current that passes through a coil, that generates a magnetic field. Depending upon the changes that happen here, it'll be accounted for by providing a counter current. If the V naught increases, current is applied such that it'll subtract a little bit of V naught to make sure it's at the level at which you locked it.
So it varies at each point of time.
As it varies as a function of time, it's corrected for. Was that?
It has to be very big.
Yeah, it is rather instantaneous. That's the whole point. That's why the lock should be on throughout the experiments that you end up conducting. Right? Yeah, it is instantaneous and the lock corrects for any deviations that might come. See, the main problem is a high result NMR would give you a very sharp resonance. If you let it move as a function of time, you're going to lose the resolution against whatever you would have gotten. Okay, why would it end up changing is because instead of having a certain value is because of any minor changes that happen right around the environment of the magnet. All right, and therefore the correction happens such that this kind of deviations are minimized.
So how this fluctuation is detected?
This is how is the fluctuation detected? We don't detect it when you run the experiment, you see the outcome. If the outcome is bad, then you realize deviations have happened. And when you correct for it, deviations don't happen, then you infer that, okay, those deviations occurred. And this has been a point that people found out when NMR began to start with. When they were able to set up experiments, they realized that if you don't lock, it's going to have drifts and you're going to lose the advantage of NMR, which is high resolution. Make sense? Why deuterium is used? I thought I discussed it. Basically, deuterium is a nuclei that's not as sensitive and it's also quadrupolar. And since you have protonated samples everywhere, the assumption might have been to make deuterated solvents would not be as difficult. You have to always sacrifice one channel to do this locking. You have to do it instantaneously as the deviations occur. So you need to dedicate a channel such that any such deviations are corrected for. You can't do it with carbon. If you do it with carbon, you can't measure carbon data. You can't do it with nitrogen, in which case you can't measure nitrogen. You definitely cannot do it with proton because you want the proton data. So you wanted a sacrificial goat in this regard, and you let it be deuterium. That's about it. Okay. Any other questions?
What is CNHT and how do we decide?
What is?
CNHT.
That's different. Okay. So I think the question is being asked. I end up using a certain variable in my pulse program where I set the const 1 to a variable called 4 and then look for 360 degree. So let me give a little bit of brief background of what was being done. So this was an experiment which had a 90-degree pulse and a lot of other things going on. So let me just put it under the ambit of water suppression so that you don't have to worry about it. And then we ended up measuring the FID. This is the overall one-dimensional proton NMR experiment that you are trying to look for. What was done here, I had a variable called const1. This is the way you end up writing it in the software of Bruker called Topspin. So what I did was that I had a pre-multiplying factor for the 90-degree pulse. So let's say it's a constant K times a 90-degree pulse. If I set the constant K to 4, what will be the pulse flip angle? 360 degrees, correct? So what I'm trying to do, if my pulse width is set correctly, then the constant of 4 should give me 0 signal. Is that correct? You would have a 360-degree flip angle. So I started with a certain pulse width, which I assumed is close enough to the 90 degrees. And I set this const 1 to 4, and I ran the experiment. And I almost get 0. Or if I get negative, that indicates that the pulse width is shorter. Isn't it? If you have a pulse flip angle less than 360 degrees, that means it's less than 0 degrees. That means you should get a negative phase, provided the 90 degrees is phase to positive, which is what you do to start with. Okay. On the other hand, if the signal was positive, then that indicates that the initial pulse width that I started with was longer. So doing this experiment, I'll be able to judge whether my pulse width for the 90 is reasonably set or not. If I get a negative signal when I set this constant 1 to 4, that means my pulse width is short, so increase a little bit, right? And then repeat the experiment to see the zero crossing. You have to repeat it until you see a zero crossing. Now the question is, why did we do a 360 degrees? You could have done the same thing with 180 degrees. 180 is also a zero crossing. Is that right? One could also ask, why did we not calibrate to the 90-degree pulse itself? That's a signal maximum. These are questions that obviously come, isn't it? The major problem with picking up the 90 degrees is that it goes with sine of alpha, which has a function that does not change much very close to 90 degrees. So picking up the maximum right close to 90 is not a very sensible thing to do. On the other hand, the zero crossing, if you're trying to look at the sine function, it goes from positive to negative around 180 degrees and negative to positive around 360 degrees. So these are, the slopes there are so much higher. So therefore, any small changes could be caught up. So therefore, I ended up taking 360 degrees. And the reason for not taking the 180 degrees is because the moment you apply 180 degrees, you're going to invert the population. The moment you invert the population, it's going to require a much longer recycle delay for the polarization to recover back so that you can carefully optimize this pulse width calibration. So therefore, if you do a 360 degrees, your D1 can be short enough for you to do quick calibration. Okay, so therefore 360 degrees is chosen over 180 degrees for a proton channel. Does that make sense? Did everybody follow what was done? So basically what I'm trying to make you understand, depending upon the hardware, depending upon the sample, depending upon the extent of tuning and matching, your 90-degree pulse width would be different for different samples. Before you start your experiment, you have to calibrate it. Why should we calibrate it? I'm sure you have seen in the last few weeks that you're doing two-dimensional NMR experiments, which have many pulses, which have variable flip angles. For instance, the DEPT experiment had one of the alpha flip angle, which could be 90, 45, or 135. So if you don't set your flip angle correctly, then you will not get the right optimization. So I just gave an example, a practical aspect of how when you calibrate the proton pulse width, you will be able to set the other pulses correctly. So basically you end up calibrating for the 360 degrees to infer the 90 degrees. If you correctly know the 360, you divide the pulse width by 4 to get the 90 degrees. And you don't do the 180 degrees because you need to have a longer recycle delay to get stuff going. Therefore, you don't have that. Did that make sense?
So what is the locking reagent for deuterated protein sample?
You would still use H2O plus D2O. Your question is, if the protein is, let's say, C13-2H labeled, you're asking whether the protein itself could be used for locking. That might not be the best strategy because a protein will be at around 1 millimolar concentration or at best at 1 millimolar. So it's not the best thing to lock it with your protein itself. So generally, we tend to have a H2O D2O mixture where the H2O is set at 90% and the D2O is set at 10% volume by volume. So this way, what you would end up doing is to use the deuterium from your solvent as lock. You will not end up using the deuterium from protein for lock because this would be having a much higher sensitivity. Okay.
So will that the deuterium in the protein affect the locking?
It should not affect as much. I know where you're taking this question. There are times where people have two different deuterated solvents in their solution. When you have, so for instance, this is an example where, let's say you had two deuterated solvents in your mixture. This would cause trouble with locking. Will you lock with DMS or D6 or D2O is the question, right? He's trying to ask a similar question when you have deuterated protein and solvent. In this case, it's a clear, obvious solution to take the deuterated solvent because if you end up converting the concentration of 10% D2O volume by volume, it's going to be significantly higher than the 1 millimolar protein that you had. You would always tend to go with the deuterium concentration that's higher. For instance, in this case, let's say that you have 400 microliters of DMS or D6 and say 100 microliters of D2O, you would realize that the D2O signal is still going to be lesser when you, because you have 6 deuteriums here versus two deuteriums here, right? So therefore, it would just make sense to go with DMS or D6. The problem would be more severe when you have a CDCl3 and D2O being the mixture. You could lock with either. What I would tend to do as an experimentalist is to lock with one and see whether the lock signal is okay, whether I'm able to shim it, and then repeat the same process with other to see where I'm able to get better locking and shimming, and then choose the deuterated solvent. Most often, these kind of scenarios won't end up coming. And especially for the protein, the deuterated protein was a deuterated solvent, I would always end up taking the deuterated solvent. And remember one thing, there is also an advantage of locking with the deuterated solvent because there is a single resonance frequency. On the other hand, for the deuterated protein, you're going to get the deuterium signal across 0 to 10 ppm. So which one will you lock on? The sensitivity is low and you can't pick one frequency to lock on it. So you're better off picking the solvent signal. On the other hand, if you're taking a scenario like this, where you have two different deuterium that you could lock in, then you would pick the one that has more sensitivity and you would go with that. Did that help a bit?
Yes, sir.
Okay. Any other questions? Okay, let's ask ourselves what all did we do the last few months. We try to understand the semi-classical picture of how a magnetization is generated for a nuclear spin active system. We ended up taking the spin half system, suspended it in an external static magnetic field B0, and then we were able to understand how the bulk magnetization ends up coming. In the same scenario, we also try to understand what is a perturbation, meaning that we end up applying an RF pulse. And how does this RF pulse end up affecting the bulk magnetization? And therefore, how we are able to collect a signal called the free induction decay. And why did we bother about it? All important information of chemical shifts, scalar coupling, etc., are all hidden within the FID, which if you're able to extract, you would be able to characterize the system. Following successfully finishing this, we went to the quantum picture of nuclear spins. And here we introduced the density matrix formalism, where we were able to convert the same things that we learned. Here, instead of looking at it in a semi-classical picture, you looked at the quantum picture. Here we said this was important to do because if you do the trace of the density matrix, the final density matrix, to an operator of our interest, then if the trace is non-zero, you would be able to get the signal of desire. We literally repeated the one-dimensional NMR experiment with the density matrix formalism to understand how chemical shifts and scalar couplings end up coming, right? From here on, we furthered our understanding by trying to use the quantum picture to use, say, multidimensional correlation. What do we mean by this? Let's say that the density matrix for the one-dimensional NMR experiment was something of the sort of exp omega I times t, and let's say ix, you ended up choosing the operator as ix so as to get a trace of sigma 1d to a as non-zero, and ended up measuring the oscillation for your chemical shift. This is what we did. Similarly, for the 2D experiment, we looked at different scenarios where we generated the density matrix of this kind, where instead of having a single time domain in the one-dimensional NMR experiments, you had two different time domains. We therefore ended up getting the final observable as exp I omega s. Anyway, I'll go to the final part. So basically, when you ended up Fourier transforming it, two-dimensional Fourier transform with respect to T1 and T2, we were able to realize that we get a signal which is a convolution in the time domain across the two different axes that you're trying to look for. Why did we want two-dimensional NMR experiments? This was done in one of the lectures, where as molecular size increases, number of protons increase. And the consequence of this is that lower resolution comes up. Not just that, also relaxation properties turn unfavorable, meaning that as the molecular size increases, R2 increases. As R2 increases, line width increases. With the number of protons increase and the line width increase, we have an overall reduction in the resolution of one-dimensional NMR experiments. So therefore, we needed multi-dimensional NMR experiments. And what we were able to see is that in one of the indirect dimensions, what was indirect about it? You don't directly measure the FID in that dimension. You allow for modulation of the directly detected FID based on the signal that you get from the indirect dimension. And therefore, you decipher the chemical shift of carbon, nitrogen that's directly bonded. Correct? And this was important because this also helps you improve. Let's say you have multiple protons that are overlapped in their proton chemical shift. Potentially, if their carbon and nitrogen chemical shifts are resolved, then you'll be able to get a two-dimensional resolution. This was the overall pretext in which we started. I hope you guys will also be able to recollect the 2D nitrogen proton HSQC, heteronuclear single quantum coherence spectroscopy, the spectrum that you end up getting from a HSQC for a protein, which has 15N in the indirect dimension and 1H in the direct dimension, has very characteristic peaks that ends up coding for the protein, meaning that every protein has a unique two-dimensional nitrogen proton correlation, and therefore one would be able to understand how the protein looks and what are the changes that come up. I showed some examples of how a protein that's folded has its characteristic HSQC, while it's unfolded, the resolution reduces in the proton dimension, and you start to see, okay, which part is folded, which is not folded, and so on. Are you guys able to recollect that? So I hope you guys all accept the fact that a two-dimensional NMR experiment is therefore imperative for us to characterize larger systems. But at the same time, as I said, 2D NMR is important. Slowly, we will also understand 2D will not be sufficient in the cases where the proton and the nitrogen, for instance, have an overlap. As much as you're able to envision, as the size increases, proton resonance start to overlap because there are too many. As the size of the protein also increases, we will be able to see too many peaks come up for a very large protein system. You remember that, right? So with that being the case, you're able to understand that as the overlap starts to increase, you need to have other dimensions in order to make sure you will be able to get the spectrum correctly determined. And therefore, once you determine the spectrum, you have the analysis going. Once you have the analysis, you have a specific peak assigned for the different residues that are being present. Did you follow that? So today we'll try to build up on the experiments that we already learned and try to see how a three-dimensional NMR experiment comes. I'm sure you guys are able to appreciate the fact at that point, the 3D experiment is going to be exp I omega I T1, exp I omega, say, K T2 times exp I omega S T3. where you have 3 time domains, and each of the time domain has a specific chemical shift. I'm just taking an example of chemical shift, but you could always encode other things like scalar coupling, and we will see how distances can also be encoded. That'll be one of the last parts of this lecture, right? So from 2D, you are able to realize how one could go towards 3D, right? Okay, with that being the case, let's move ahead and understand a little bit of what is the overall architecture of the backbone. So NH. This says I'm off proteins for a very long time, but anyways, N, C alpha, H alpha, R, C double bond O, and it keeps on going. So this is the basic monomeric unit of a protein. Where R is the side chain group. Right? So this is the monomeric unit of amino acid. And as you're able to realize, there are protons at appropriate positions. I'm not sure how many of you would have taken a biophysical chemistry course. One would understand the angle subtended by the NHCO is more or less in that trans orientation, meaning that the carbonyl and the H would be trans with respect to each other. Peptide bonds, this is called an omega angle, are almost always in the trans dihedral angle. All right. On the other hand, whatever you end up getting in the phi and psi, which are also called the Ramachandran angles, you would end up getting information on what are the conformers adapted by a given monomer. Okay, so therefore, if you are able to pick up some chemical shifts for each, and remember, as this dihedral angle changes a little bit around these atoms, their chemical shifts also be sensitive to small changes in the electronic environment. So therefore, as a protein starts to adapt different conformations, you're able to understand how the nitrogen-carbon chemical shifts would end up varying. This is what gives you the resolution when the protein is folded, because they end up sampling different phi-psi angles. Right? So slowly we are also able to understand that if we get the chemical shifts of all these, we will be able to understand what kind of system that we are dealing with. Right? So in order to do this, you want the chemical shift of this proton, and then this proton. If you guys might recollect what we learned from the hardware portion, you might remember that the signal to noise ratio is proportional to gamma E power 1 and gamma D power 3 by 2. Excited power 1 and detected power 3 by 2. And what does this say? If you excite a proton, go to nitrogen and detect back in proton, you have the most sensitive experiments. And how would you end up going from the proton to nitrogen? All of you, I'm sure, are quite confident you can either do a SQC kind of a transfer or a MQC kind of a transfer, right? A HSQC will end up taking the HZ to something like 2HZ NX or NY. And therefore, you get the frequency labeling on the nitrogen. Finish that, do the reverse synapse to get it back on the proton. Therefore, you would have the proton resonance intensity modulated by the nitrogen frequency, which you infer from the interferogram, Fourier transform, and get the proton and nitrogen chemical shift. This is the HSQC. Similarly, you can do an experiment between the H and C, where you repeat the HSQC type experiment to get the chemical shift of H alpha and C alpha. All that I've done so far is to repeat what we have done before to put into context of how we are going to build bigger experiments. Okay. So in this aspect, what I would like to do is to make you guys understand, okay, if I start from proton, go to nitrogen, and from nitrogen, if I go to this carbonyl and then get the frequency and then go back the same way, I'll be able to stitch a 3-dimensional NMR experiment. Is that true? So basically, that's what is the entire idea here. Basically, you start with a proton and then you transfer it to the nitrogen, right? And in the carbon, you don't do anything. And then at this point of time, you would have generated something like 2HZ NY, right? So if you stitch yet another inept here, where you do apply a 180-degree pulse on the carbon, right? There's something that we need to mention here. This is tau. And this is tau prime, let's say, right? And then you have a 90-degree pulse. Of course, I'm just putting a Y face again. so that we generate a single quantum coherence term. And therefore, what you end up generating at this point will be something like 4 HZ NZ CY, right? If you go back and reflect on what you did for your mid-semester exam, this was one of the questions. Okay, the idea was to say when you transfer from one to the other, what do you end up getting? All right, so this is one inept, this is one inept transfer. This is the other inept transfer. These are all based on single bonds. And of course, what you're going to do here, set this tau 1 over 4J NH, where JNH is approximately 90 Hertz. Immediately the question arises, what should you set tau prime to? The answer is easy, 1 over 4 times JNC coupling. So what is the magnitude of this coupling? As much as you are able to realize, as you start to have atoms that are of lower gyromagnetic ratio, their scalar coupling starts to reduce. For instance, you might remember JCH spanned something like 125 to 220 Hertz. That's because carbon and proton, carbon has a higher gyromagnetic ratio than nitrogen, so therefore ends up having a higher scalar coupling constant. So the moment you are able to understand this, you see that a nitrogen-carbon coupling will be less than even 90 Hertz that you end up having, right? So let's take a look at this, just one moment. So let's go to the classroom. What I have done here is that I've updated one of the stellar reviews written in this regard. I'm not trying to say this is the easiest of reviews to read because there are some concepts that I'm not taught from this. Basically, they're employing something called pulse field gradients. Just one moment. Okay. The entire thing relies on something called pulse field gradients, which I've unfortunately not had the time to go through. Okay. But overall, the idea would remain the same. So let's first go here and understand some important aspects. So this is the spin system for a peptide backbone, as you're able to see. What does a spin system mean? You're just putting the bare backbone atoms that are being present, and they're jotting down the one bond scalar coupling values that exist. Are you guys able to see that? Right? So one of the JNC coupling values that you're trying to see, you're immediately able to realize these are actually smaller in magnitude. So about 10 to 15 Hertz is all that you have for an NC coupling. Right? So therefore, slowly what you start to appreciate, yes, you started with something like 100 Hertz, but you're going quickly to tens of Hertz, lower tens of Hertz, right? So this immediately indicates that the transfer time here versus here are vastly different. While this entire transfer time is around 5.5 milliseconds, you would realize that since the coupling is going significantly lower, it's going to increase to several tens of milliseconds. Did that make sense? So slowly, a lot of other things start to happen. What are the other things? You realize that as much as you believed relaxation did not happen or affect much in this 5 milliseconds, slowly relaxation will start to play a role. As much as you want to transfer to as many atoms and get as many frequency labeled, you cannot do it infinitely because you're going to lose coherence due to relaxation that happens while you end up implementing this experiment. Right? So this is the flip side of it. The advantage of it is that you get higher resolution. The flip side of it is that you're going to lose sensitivity. Did that make sense? Right? Anyways, so, but thankfully, nature has been nice enough for us where these transfer times are not that long for the coherence to get completely destroyed. You could still successfully transfer it. And now, if you have transferred it to carbon channel, carbon chemical shift, now what would you like to do here? Get the chemical shift of carbon in the T1 axis, for instance, right? The moment you get the chemical shift of carbon, the next step would be to transfer it to nitrogen, get the chemical shift of nitrogen, transfer it to proton, and then detect it in proton and T3. That's the overall experiment, right? You have two reverse inepts because you have one inept, reverse inept for the proton to nitrogen, going from nitrogen to proton, another reverse inept for nitrogen to carbon, which has to be converted back from carbon to nitrogen. Similarly, as you started from HZ, went to HZ NY and 4 HZ NC CY, you'll go back from here to here and here to here in the reverse inept to make your signal detectable. So basically, the idea would be to put inerts next to each other and go to the signal of interest, and therefore you'll be able to understand. So if you take a look at it, they're going to give you ideas of how to label the protein. This is one of the well-cited reviews from 1990s. If you see, this was published in late 1990s. Not the most latest, but most of the experiments that are shown here would suffice for you to understand what's going on. I'll also take the Kavanagh book to get this done. Okay, so let me go here. There are some important aspects that I end up showing. So there you go. So this table is a very important table. We will see what these experiments are in one moment. Maybe I should show that and then come forward. The nomenclature of these experiments is based on the names of these spin systems. Basically, you have HN proton, which stands for the amide proton. You have H alpha proton that indicates the proton attached to C alpha, the chiral carbon in the amino acid. N stands for amide nitrogen. C alpha stands for the C alpha carbon. Okay. Instead of writing C alpha, they end up writing Ca. Instead of writing H alpha, they write Ha. Okay. So the most obvious experiment to do would be something called, which is what we started discussing, the HNCA experiment. What do we mean by this? This is an experiment where you start from the proton, go to nitrogen, go from the nitrogen to go to the C alpha carbon, right? In whichever dimension, get the C alpha chemical shift, get the nitrogen chemical shift, come back to proton and finish up. Why did I say whichever dimension? You don't have to commit that whichever nuclei you finish at the last, you need to get the chemical shift. For instance, you could do it in a way where you go from proton to nitrogen, get the frequency labeled of nitrogen first, then transfer to carbon, get the frequency labeled of carbon next, transfer back to nitrogen, transfer to proton to get the frequency label of proton. Did whatever I said make sense? You can transfer and get the chemical shift, or transfer and then get chemical shifts back and forth to get it done. The alternate way would be you transfer from proton to nitrogen, transfer to nitrogen to carbon, and you get the frequency label of carbon along T1, transfer back to nitrogen, get the frequency label of nitrogen in T2, and you could transfer back to proton to get the frequency label of T3. Did that make sense? Right? So you could either get the nitrogen in T1 and carbon, sorry, C alpha carbon in T2, or you could get C alpha in T1 and nitrogen in T2. You could do it either ways. We'll see what kind of ways that people follow. But overall, I hope you guys are able to appreciate the fact it's just a series of inerts and frequency labeling to come back up. One of the questions that was asked in quiz 2 was to make you guys understand, while going from 1D to 2D, yes, you lose sensitivity, but you get resolution. But more important aspect also is that as you go from 1D to 2D, you're also spending a lot more time to get your data. You have two different chemical shifts that are encoded. For each, you need to do quadrature. As much as you have to repeat the two-dimensional experiment at least 2 times to get the indirect dimension frequency. In this experiment, since you have 3 dimensions, you have to repeat the experiment at least 4 times to get the indirect dimension frequency of, say, carbon and the indirect dimension frequency of nitrogen. So the experiment time also increases significantly. Did that make sense? Okay. What these guys have nicely done here also to show how when the experiment is done, the sensitivity also changes. Of all the 3-dimensional NMR experiments, one of the most sensitive experiment for proteins is the HNCO experiment. CO stands for the carbonyl carbon. As much as you can transfer to one, you can also transfer to the other. Okay, and the important thing to note here is that why is that the most sensitive experiment? You see that the scalar coupling between the NC is slightly higher than the NC alpha. Right? The NCO coupling is 15 hertz. Well, the NC alpha coupling is about 11 hertz. Right? I mean, ask what might 4 hertz do? It makes a huge difference. Calculate 1 over 4 times J, where J is 15 versus 15, 11 versus 15. You'll see how much difference that you're able to see. Okay? So therefore, generally what people tend to do is to benchmark the 3-dimensional experiment that correlates the HN and CO chemical shift as the most sensitive experiment. Okay. So that is what is being done here. What they are able to make you understand is that when you run a HNCO experiment, it ends up correlating the amide proton to amide nitrogen. The I indicates which residue you're talking about. If you have a polymer, you have multiple residues that are being present. If a general index is given for a given residue is I minus 1 indicates the preceding residue, I plus 1 indicates the succeeding residue. Make sense? And what this is trying to tell you, the nuclei that is being observed is that if you correlate the amide proton to amide nitrogen of the ith residue, the carbonyl of the preceding residue is what is frequency level. So basically, this is an experiment. So this is a monomer. This is a monomer. So this is the ith residue. This is I minus 1. Of course, you have an I plus 1, which will be once again the C prime, N, H, C alpha, and so on. Correct? So what they're trying to make you understand here is to also show you which nuclei end up correlating with each other. If you have HN of I, N of I, this is an experiment that correlates with the C carbonyl of the I minus 1. So that experiment is called HNCO, 3D HNCO. Why is it called HNCO? It correlates amide proton, amide nitrogen, and the carbonyl carbon. Okay, so from here on, I'm going to use such names to indicate 3D experiments. Okay. The next immediate 3D experiment, which comes to our head, is also the HNCA experiment. What is the HNCA experiment? The HNCA is similar to the HNCO. The only difference is you correlate H, N, and C alpha. The super interesting aspect of this experiment is that unlike the HNCO, where only the correlation is done with the preceding carbonyl carbon, in this case, you correlate it with its own C alpha and the preceding C alpha. So what do we mean by this? It not just correlates with its own C alpha. I does not just correlate with I itself. It also correlates with I minus 1, which is what? Is about 7 hertz. Now you might start wondering, why are we trying to do something like this? What do we mean by correlate? This is what we mean by correlate. Here we are correlating chemical shifts, isn't it? By this, what do we mean is that in a 3-dimensional spectrum, you will only get a peak when the H and C are single bonded to each other. The H is bonded to a nitrogen with a single bond, nitrogen is single bonded to the carbon in a single bond. That's when you get a signal. Take an example of a 2D experiment where the only whenever you had H and N bonded, you get a peak. If H is bonded to C, you didn't get a peak. If H is not bonded to C or N, you do not get a peak. That means it's not correlated at that point, right? So here what we are talking about is that only when you have the H correlated with N and the N correlated with C, you're going to get a signal, right? And how are these correlations established? They are established by a single bond scalar coupling that exists. The magnitude of scalar coupling determines the sensitivity of experiment. And as has been rightly done here, the N amide nitrogen to C alpha of the same residue is about 11 hertz and the preceding residue is about 7 hertz. So if you end up doing an experiment where it's optimized, let's say at 9 hertz, you would not just get the HN correlated with its own C alpha, you'll also get it correlated with the preceding C alpha. So you'll get a peak for 2 reasons, not just for the H and C alpha, where everything is I. We'll also get a correlation for H and C alpha, where it's I minus 1. Make sense? So now what is the advantage of this? We just saw in a HNCO, you got I minus 1. Why are we complicating by having too many resonances? Could be one question, right? So in order to understand this, we need to understand a polymer. So let's say this is the first residue, second residue, third residue, and fourth residue. Remember, when you acquire HSQC, the labels for each resonance belong to which residue is not known. You only see a signature, how it looks, but you do not know which peak belongs to third residue, fifth residue, 50th residue, and so on. We need to find that. How do we find that is this entire idea here. Okay. In the HNCO experiment, what you're going to get, let's say you're correlating H and N of 2, the second residue, you're going to correlate to the C prime of the first residue. This is what the HNCO experiment will correlate, right? On the other hand, the HNCA is going to be super interesting. HNCA will give you H of 2, N of 2 correlated with a C alpha 1, but also CA of 2, right? Remember that experiment will also correlate H of 3, N of 3 with CA of 3, but also CA of 2, right? Slowly you start to see we have a bridging gap where if you put it all together, you'll be able to nicely string across all these resonances, which nitrogen belongs to which C alpha, who is its predecessor, and who is its successor, slowly if you put it together. Okay, I hope this gives you an idea when you have a long chain polymer, how this three-dimensional NMR experiment of HNCA will help you get assignments for every residue, right? This is essentially how we end up getting the chemical shift for each in the two-dimensional NMR experiment. Okay, so slowly it goes to the fact that now there could be multiple experiments. You could also somehow design an experiment where instead of going from the HN to both C alphas, you could have an experiment where if you pass through the carbonyl carbon, so what do I mean by that? Let's say instead of jumping from the nitrogen to carbon directly, if I somehow route it through the carbonyl carbon, this will not be picked up because there is no carbonyl carbon, right? So that experiment is called the HNCOCA, as you're able to see. The CO is set inside bracket, indicating that you will transfer the coherence or polarization through it, but you will not do frequency labeling. So this is still a three-dimensional NMR experiment where the HN is correlated only with the C alpha of the predecessor. So slowly what we're able to see is that if you have the grip on designing experiments, you could specifically design experiments where the coherence will travel the way you want it to travel. How do we end up achieving? I'll try to show it as we go forward, right? Of course, as you start to slowly see, whenever you set up a compromised J delay, what is a compromised J delay? For the HNCA, you have to choose between 11 Hertz and 7 Hertz. And I said something like 9 Hertz, right? So therefore, you get a sensitivity for the intra as 50 units. And the previous one is 15 units. Meaning that since you have lesser scalar coupling, you're going to have less signal for one versus the other. You can still tune it. This experiment is still tuned towards the intra peak than the inter peak. Inter meaning I to I minus 1, intra meaning I to I, right? On the other hand, if you tune this experiment through the carbonyl, you can still get a better sensitivity. That's because you're only selecting one pathway, so you can ensure that the maximum sensitivity comes. This also is because of the fact that you transfer through the 15 and 55 Hertz coupling, which are probably reasonable compared to the 9 Hertz coupling. The transfer times would be still better to get a better sensitivity. Okay, slowly what I'm trying to make you understand is that with the power of the density matrix formalism, you would be able to come up with specific pathways for the polarization and or the coherence to travel and therefore pick up chemical shifts that are specific. Okay, good, right? So I'm not going to go into much of details. This is yet another example of another experiment, similar to the fact that you can go via the HNCO, the previous experiment is a preceding carbonyl. You could also do an experiment called the HNCA-CO, where the CA will just jump, will not do frequency labeling. Okay, we'll just transfer through it. You just do an inept through it, but you will not do frequency labeling. Only when you do that, you waste time and you lose relaxation, right? On the other hand, if you transfer through it, you waste less. So therefore, this is one experiment where the HNCOCA correlates the HN with its own carbonyl. So therefore, if you're able to use the HNCACO and then the HNCO together, you can repeat the process of whatever I just mentioned. Any questions, please raise.
How can we jump down with carbon coupling adjusted carbon? How we are going to,
It's through the scalar coupling. I'll come to that point. Maybe I'll touch that tomorrow, because if I tell that right now, it'll be confusing. So the question that Shivam is asking, which is a very valid question, is that when you're applying a pulse on carbonyl, why does it not affect the C alpha? Because it's the same channel. Correct. So it's a very valid question. Maybe I can give the answer. It's within this itself. The interesting aspect is that within a protein, the aromatic comes up here, the aliphatic carbon comes up here, and the carbonyl carbon comes up here. Okay? You can apply pulses which only excite specific portions. These are shaped pulses, which once again, unfortunately, I do not have time to do, or even something called off resonance effects for even for rectangular pulses, which you can carefully tune, where only the carbonyl will get excited or inverted, while the C alpha remains in its equilibrium. You can do the opposite also. Okay, so as you start going forward, you're going to see pulse programs where the two carbon axes will be treated separately. So this is the example pulse program of the HNCA or HNCO. The programs are actually very similar. So you end up choosing, if you end up choosing for the excitation to be in the carbonyl carbon, which is C prime, then the decoupling will be done in C alpha. Okay, since their chemical shifts are different, although they are actually the same channels denoted as separate channels. And you end up implementing the experiment, it's done in a different way, right? It's actually the same channel that you apply the pulses. So what I request you guys to do is to go take a look at the Kavanagh book, chapter 7, which talks about the heteronuclear NMR experiments. And not just that, I think it's frozen. Okay, not just that. The most important aspect that I want you to look at, let me see whether I can go to that page. This is heteronuclear correlation, which you have seen HSQCs. These are the examples that we saw even earlier. So take the book and read how does a HSQC work. So here, the nice aspect of it is that they would have had very nice tables to make you understand. So this part nicely shows you what type of correlations are established. What does the HNCA achieve? What does the HNCOCA achieve? And what are the chemical shifts, scalar couplings that are invoked? My request to you guys would be to go and take a look at this. This is not being rendered properly, but otherwise in the textbook, it looks very nice. Try to get an idea on what are the nomenclatures given for these 3-day experiments so that you can see these pulse programs tomorrow and get an idea of how every atom that are NMR active within a protein are given a chemical shift using 3-dimensional NMR experiments. Okay, that will be our task. With that, that's all we will do. We will not do a practical aspect of it because we won't have time. Okay. All right. Thank you very much. See you guys tomorrow.